Okay, but you guys should all have I sent an updated exam with the key, so hopefully you guys should have that at that point. As a reminder, regrade request forms are on my website. If they're not on the Organic 2, they're on the Organic 1, which again I won't be able to update, but they should be on the top of one of those two. Again, please get those to me for quiz 1, quiz 2, and first exam by next Friday, November 1st. We also have a quiz 3 is coming up next week, and quiz 3 is going to include 3 different types of questions. The first one is going to be on sort of aromatic molecules, right? So are these molecules aromatic? Are these anti-aromatic? Are they neither? And so we went over that last class. You guys should feel comfortable with that. The other 2 components are going to be on mechanisms and synthesis, so there aren't going to be the sort of reaction one. So I guess the is it aromatic is going to take the place of the reactions, but in essence, synthesis is kind of reaction. So the synthesis questions will incorporate chemistry that we're going to learn today and Wednesday. Okay, so hopefully it'll be clear what some of the interesting things are about reactions of benzene as we go through the next couple classes. So there's a lot of reactions in benzene. I'm going to sort of distill it a bit. So one of the things that we talked about last week, I'm just going to sort of mention this fairly briefly. We mentioned that that phenol is fairly acidic as compared to other standard alkoxides. pK is about 10 or so. So you can deprotonate that fairly readily. Using sodium hydroxide or using sodium hydride or something of that sort. And what will happen, right, is you'll get to the phenoxide. And the reason why I want to bring this up is that we discussed previously, a phenol is, when you look at this phenoxide here, when you're trying to compare it to things that we've seen in the past, right, it does have a little bit of, is it an alcohol, right? Is it an enol, right, or enolate, I should say. And so, much like we learned with enolate chemistry, right, you can potentially react at this carbon or this oxygen. Okay. Now, as it turns out, as the sort of book describes, I just want to tell you 2 different types of reactions. Phenols, generally, we'll talk about substitution of benzene in maybe 10 to 15 minutes or so. But it turns out that because the phenoxide is so stable, usually when you have an alkoxide, you treat it to your generic or your standard, alkyl halide, for example. You're not going to get C alkylation, you will get O alkylation. Okay, so in this way you will generate some type of alkyl group. And if you look in the book discusses things like methyl triflate type molecules or alkyl halides. A classic example, though, of C alkylation, it's perhaps worth mentioning, synthesis of salicylic acid. Right, and this will, right, this is ultimately going to be C alkylation. I don't know if this is kinetically or thermodynamically controlled, but you can certainly imagine that if carbon dioxide reacted with the alkoxide, that could break back down. That sort of addition of CO2 across that bond could certainly be reversible. Sorry, here, citric acid. And so can C alkylation, but that's going to be a little bit less likely to do so. And so, as we sort of discussed in the past, if you heat reactions, you can get CO2 to go away. This is a situation where you potentially just take some dry ice and throw it in the reaction or bubble a balloon of CO2, and you can get the salicylic acid. Right, and this is just sort of classic chemistry in part because, this is the synthesis of basically aspirin, right? So if you take this molecule and treat it with something like acetic anhydride, right, you can actually get to aspirin. So this is aspirin. I'll say acetic anhydride or something of that nature. You can actually isolate this into acetyl salicylic acid, otherwise known as aspirin. So it's sort of worth just pointing out briefly that, because we did talk a little bit yesterday about alkoxides, phenoxides, and the ability to deprotonate phenols. In general, if you treat these with alkyl halides, you're going to get O-alkylation. Classic example of C-alkylation, though, is sort of the Kolbe synthesis. You guys should be able to do the mechanism of this, right? Just to sort of go through it. All right, what's going to happen? Right, it's going to basically be enolate chemistry. And as we're going to see, a lot of the chemistry of aromatics are sort of, are certainly be related to alkene chemistry, for example, and certainly enolate chemistry is sort of comes from, in many ways, alcohol chemistry. Trying to think what we have in solution here. I'm just going to show an intermolecular proton transfer here. It's going to ultimately re-aromatize. Could be phenoxide in some way. This is the reason why I was hesitating to do this, as you might imagine, if I were to do that. All right, that's probably not going to be. It's going to get another proton transfer, right? But regardless, we're going to do the acidic aqueous workup at the end. So something's going to deprotonate that, redrive aromaticity. I just showed it intermolecularly, but then it led to a molecule where, in principle, this would probably then want to deprotonate that, because obviously a carboxylic acid is more acidic than a phenol. But yeah, so again, if you want to use phenol to do it, that's fine as well. But then obviously you acidify that and you get there. So these are just some examples of functionalization of phenols that I wanted to take you through. I do want to, before we get into some of the meat and potatoes of benzene chemistry, I do want to discuss one more group of reactions. And this is sort of benzylic chemistry, and I'll try to put it in perspective a bit. So we've certainly seen, right, so when we talked about alkenes a little bit, right, we talked about kind of how groups that are kind of at that carbon next to alkenes is allylic, right, and we've talked about, right, that would be an allylic proton. Right, and this guy here, this would be benzylic. Okay, so we talked about how when you have an alkene, due to, for example, when we talked about halogenation, we talked about how, for example, stability of radicals at that position is a little bit more stable than your typical carbon because of resonance. Likewise, chemistry based upon benzylic positions is similarly different than your typical carbon-hydrogen bond. And so it turns out that you can do some chemistry that's some that you'd probably guess based upon what we saw before, right? So a lot of chemistry that we saw on allylic protons, for example, we saw halogenation, allylic halogenation, right, as an example, when we use like NBS and light, or when we use bromine and heat, or chlorine and heat, right? We would go through radical-based processes, right? And you can make, benzyl bromide, benzyl chloride, and so forth. And the book talks about a few other things that I'm not going to go into, but it talks about how like certain oxidants can oxidize benzylic positions. I'll just mention one that I thought was kind of interesting. This happened to me. It turns out that you can actually, do you guys know what that molecule is right there? Benzene with the methyl group on it. Probably used it in the topic class. Yeah, so that's toluene. It's a pretty common solvent. It's a little bit more safe than benzene, even though it's just got that methyl group and it looks very similar to benzene. It's generally a much safer version of benzene. It's a little bit less volatile, but that's not the whole picture. Benzene, if you think about benzene, your body, when you ingest things, or when you come in contact with things, right, your body wants to sort of break them down. And your body does this through a lot of sort of highly reactive, especially oxidative processes. And so there's a lot of oxygenation and so forth that takes place, sort of metabolism, right? It turns out that benzene, because of the aromatic stability that we talked about, it's going to be very difficult for your body to break down benzene. And so whether it's something you guys will probably learn about in biochemistry, DNA intercalation, right, which can lead to mutations, or when you try to look at this molecule and you think about what types of oxidation pathways could take place, it's fairly common, for example, for epoxides to form, and your body is basically one giant nucleophile, and so that could then alkylate DNA and so forth and start leading to problems. When it comes to toluene, you'll get to it'll be much quicker, and it'll be much, you'll start to oxidize to things like benzoic acid and benzyl alcohol and benzaldehyde, in part because of that benzylic position. You can sort of imagine this again, much like the allylic position. You can imagine a lot of these processes potentially taking place through radical-based processes. Not entirely accurate for all of them, but certainly you can certainly rationalize that in that way. So the ability to have a much more easily oxidizable carbon-hydrogen bond will lead to oxidation products that look more like this. And these are a little bit more forgiving on your body, right, than these much more highly reactive epoxides. And in addition, this is a much faster process, so your body can generally clear out toluene a bit faster than benzene. Yeah.
Before you get to the alcohol, do you have to do a...
We're not going to talk about the mechanism of benzylic oxidation. We can maybe talk about it very quickly.
I was just wondering if you needed to brominate.
No. We're not. I'm not talking. I'm just giving an example of physiologically systems that I thought was interesting. That I remember being an interesting discrepancy between benzene and toluene when I was going through my formal studies. That I thought sort of would, which is maybe tangible to you guys, and that I think helps explain the oxidation potential of these sort of benzylic protons. Another example, because toluene is a common solvent, and when I was in grad school, I was in a lab that did a lot of high temperature reactions. We still do quite a few of high temperature reactions in our lab, but I was up at like 180 or something like that. I forget. I was at a really high temperature, and I wasn't one of the people in the group that often did high temperature reactions. Other people on a specific project were doing them, but I happened to be running a high temperature reaction in toluene, and I started getting a lot of these aldehyde protons. And I was like, what's going on? And I was just accumulating a whole bunch. And you guys know aldehydes by NMR are very distinguishable. So I would get these singlets by NMR and, basically getting sort of oxidation products. So I switched to benzene and I didn't get these problems as much. So this is just an example. You could certainly, as we've talked about oxygen a little bit, right, you can sort of imagine oxygen as the sort of diradical, right, which is the sort of triplet state, which is what it more reasonably exists as. And so you can begin to get to organic peroxides, which should subsequently break down to those aldehyde byproducts. So, Abraham.
Is there an NMR machine that spits out the product for you?
NMR machines don't spit out products. So automated NMR interpretation. I'm sure people are working on it. I'm sure it exists. But I could spend forever talking about how I don't want to get into it. I'm going to move on. Interpretation of NMR is critical for organic chemists, and I imagine it will remain critical throughout my lifetime. Okay, so one last sort of point about benzylic chemistry that I think might be interesting. We've talked about protecting groups a little bit, right? And so we talked about, for example, if you want, so in order for things to be good protecting groups, right, you need to be able to put on the protecting group, and then you need to be able to take off the protecting group. And so we've learned a few examples of this, right? So for ketones, aldehydes, and so forth, we've learned that, for example, we can add, we can make ketals or acetals, right, under acidic conditions. Here's just an example of one with ethylene glycol, where you take ethylene glycol, you treat it with some acid, and you get this cyclic acetal, ketal, I should say, that we put here. You could do all the chemistry that might ordinarily react with, right? Do all the chemistry that you might ordinarily react with ketones, and then sometime later on in the synthesis, you can remove it. All right, let's say, for example, acid and water, right? You can get back to your ketone. But obviously, the first one that we learned about was alcohols, right? And the classic example of an alcohol that we've seen protecting groups would be silyl protecting groups, right? So we often just said TRS chloride because there's so many different types of silyl protecting groups, and we sort of talked about how, depending upon the nature of them, some of them can be more labile, some of them can come off easier, some of them can stay on under much more forcing conditions. But the nice thing about silyl groups is that silyl ethers, right, is that in general fluoride sources, right, can generally, which we don't often use fluoride chemistry that much. I guess it's changing a little bit nowadays, but classically fluoride is not the most commonly used reagent, and so aqueous workup, for example, you can sort of get back to these alcohols. Right. What we didn't necessarily talk about was sort of orthogonality. What do I mean by orthogonality? What I mean is if you have, say for example that you would have two alcohols, right, or you're going to put on a protecting group onto one alcohol, then you're going to generate another alcohol, you want to put a protecting group onto that one, right, that you can deprotect under different conditions. For example, let's say, I'm going to have to ask for a marker or something soon. So let's say, for example, that we had, let's just say that we had a molecule like this, right, that had sort of two alcohols on it, right? And let's say that what we wanted to do was put a TBS group right? Mean or something like that. Let's say, for example, that we wanted to put a TRS group and we wanted to put it at that carbon, right? That's gonna be a tough, tough thing to do, right? Because a TBS group is big and bulky. If you were going to get selectivity for one over the other, right, it would probably be, right, the less sterically encumbered if you were looking for some type of selectivity of silating one alcohol over the other. In fact, there's conditions that you can use with specific Lewis bases, which can make it even larger and get that selective protection. But that's going to be really hard to do, right? You're probably more than likely going to silate that one, right? And so the question would sort of become, well, I want that for whatever reason, a synthesis problem. How would I want to put that on there? Yeah.
Would it just be like a 50-50 kind of
50-50 kind
thing?
of thing?
OPR is
Well, no, because maybe if you're really lucky, but in general, the silent groups are big and bulky. They're going to prefer the more sterically accessible ones. So just hear me out. You'll understand once I hopefully get through this. So what you want, right, is you want to be able to put on a protecting group that's going to stay on, right? What you want to be able to do is you want to put on a protecting group that's deprotection conditions are going to differ from the solid group, right? So you want something that you can take off, but it's not going to be, for example, under fluoride sources, and hopefully not under some various conditions. And a classic example, right? Classic example of another protecting group that deals with benzylic chemistry is benzyl halides. And so, this isn't probably going to be the best. I'm probably using a bad example here because this is not quite as bulky as it's probably not as bulky as a TBS group, so your selectivity here would not be necessarily great, but hopefully you guys can understand the spirit behind what I'm trying to get through here, right? So if it's going to be very difficult for you to get this because that's not going to work, right? Maybe you could take advantage of sterics of this system, right? And just assume that the more accessible one is the one that you're going to be able to functionalize first. That should make sense, right? Even if in actuality you're going to have some challenges, you can imagine that sterics is something that you could take advantage of, maybe if it's not exactly in this setting, right? So we would maybe, bless you, maybe we would treat this with some base, sodium hydride, followed by benzyl bromide, and one equivalent. And maybe we get a bit of selectivity for that molecule there, right? Just based upon sterics. Whether or not we really would or not is I'm not going to worry about that. We'll go with the spirit of it today. Okay. Now what you can do is now you can put on the silyl group. And the benzyl groups can come off. One of the things about benzyl groups is there's a few different ways that you can take off benzyl groups. So one of them would be under like harshly acidic conditions, like like strong acid and water. Right? We've seen, for example, that you can cleave ether bonds with acid and water. But benzyl groups are kind of special in that you can actually hydrogenate them with hydrogen and palladium on carbon. Okay, and I'm not going to go through the mechanism of this, okay, but in general what you can do, and this is well known, is that you can actually add hydrogen basically across that bond there, such that the byproduct would be toluene. Okay, so this is another really common protecting group. So I think the point that I want to make here is that unlike your typical ether, benzylic ethers can oftentimes be fairly special. Because you can actually cleave them using benzyl. Basically, you can cleave these benzyl ethers with hydrogen and palladium on carbon. Okay, that makes sense. So don't worry about the mechanism of this as much as the fact that it's another example of a benzyl group being kind of useful and special. And again, I get spirit of this is what I'm trying to get you at, even if maybe the selectivity wouldn't be as good as I perhaps try to get there. Okay. So this is just another protecting group that you guys could use. Okay, and so that's going to be pretty much it for sort of the more benzylic stuff. The remainder of the chemistry that we're going to talk about within benzene chemistry. We're going to talk about electrophilic and aromatic substitution chemistry. Okay? And before I get into electrophilic, nucleophilic aromatic substitution, I want to sort of go back to the end of last class really quickly. And I ask you guys if you could, for example, and this is one of the things that at this point in the course is going to be beneficial if you're getting better at this, especially with aromatic chemistry. Right, the sort of idea that, you know, perhaps pushing lots of the ability to push lots of electrons back and forth, right, and sort of through multiple pi bond systems. So when you have this sort of network of conjugated alkenes, there's a lot of chemistry that can take place through these conjugated systems, and your life will be much. Where's your life? Your problems, particularly with some of the aromatic chemistry that we're going to talk about now, will be a lot easier if we can imagine pushing electrons through multiple bonds at the same time. So this is something that you really want to try to get comfortable with at this point if you're not already. All right, and this is an example of a few different forms of sort of a molecule called fluorescein. Right, and we can in fact go back the other way as well. Sort of open that. Right, and you can go back and forth. And so this is just an example that I gave you guys at the end of the last class to try to get you guys to sort of practice sort of pushing arrows through more extended conjugated systems. And so hopefully you guys can be sort of begin to get comfortable with this, right? And from the standpoint of, in some cases you could break them down. In other cases it would be a little bit more difficult, right? Like in this case, if I were to push the arrows here, I'm breaking the octet rule, right? So I have to push electrons somewhere, and the only ones that I could really move are those lone pairs, right? Now if I wanted to break this down a little bit further, I could put that lone pair at that carbon, right? Draw the molecule, and then continue to push those electrons back up here, and effectively what I'd be left at is sort of like an allylic anion, right? And then a subsequent another allylic anion, and then another allylic anion, and sort of shift between one to the next. In the reverse, it would be perhaps a similar scenario where we would maybe view this as an enolate, and we push the negative charge up here, right? We'd then have to draw that one, right? Which would then put another allylic anion there, which would then undergo an E2, or an elimination type process to ring open that ring here and create the acetate. And so that would effectively triple the amount of work that you would have to do if you were going to have to redraw each and every one of those intermediates. And so the point that I really wanted to draw home here is that, we will see mechanisms, and certainly once we start getting to pericyclic reactions, we'll see them as well, where it's going to be important that you guys can sort of see multiple series of electrons moving at the same time and doing it without necessarily screwing things up. Okay, and this is going to take us into sort of reactions of benzene. Okay. All right, so we're gonna learn about two types of reactions. The most thorough of them is going to be electrophilic aromatic substitution. Okay. Okay, and electrophilic aromatic substitution basically means that we're going to take an electrophile, treat it with an aromatic molecule, and we're going to get a substitution of that molecule. Okay, we're gonna. Okay, and so in general, what we're going to be talking about here is a reaction in which case we take an aromatic ring, benzene, virtually always benzene. And as we're going to see, we're going to actually substitute out one of the protons on that ring for that electrophile. Okay, so E is just being very generic here. We're going to spend some time today talking about the different types of E's that we'll be making and what some of the different groups are that we're going to bring in there. But what's important to recognize, I think, is a lot of the chemistry that we're going to see is going to be mechanistically related to reactions of alkenes, right? We've seen alkenes behave as nucleophiles, right, quite a bit. And so that's kind of what we're going to see is going to happen here, is that the double bonds in the benzene are effectively going to serve as nucleophiles, right? And then we're simply going to do a kind of a sort of second step of the elimination sort of E1 reaction and effectively go back to our aromatic species. Because of that, benzene is you know, one of the things that differentiates, in addition to the fact that we're going to regenerate aromaticity, is there's a stabilizing factor, right, of benzene that we talked about. That's the whole point of the aromatics, right? They're more stable systems. So as we'll see, you oftentimes really need to soup up your electrophiles in order to get them to react with aromatic rings. Okay. So a classic example of this, right, would be, you could imagine a scenario where you took bromine, as just a more specific example, right? And let's imagine that same mechanism. I'm just going to start with this and sort of explain some subtle differences here. If we were to imagine this reaction taking place with bromine, right, we would imagine that this molecule will react. And rather than go to the bromonium, right, I'm just going to keep it as the sort of open form, right? So we could certainly make that bromine carbon bond and put the positive charge on the bromine. But for the sake of saving space, right, then we're going to re-aromatize by putting this there, right? And so if you took benzene and you treat it with bromine, you could certainly imagine a mechanism that would go through this process that I'm showing you here. Now the issue is that if you did try this reaction, if you did try to take benzene and treat it with bromine, they're not going to react with one another. It's going to be, well, some benzene derivatives that are really electronically rich will react with bromine, but for the most part, benzene itself, for example, won't react readily with bromine. What you need to do is you need to make the electrophile better, okay? And the reagent that we do there, get out of the way. The sort of reagent that we use to help this is some type of Lewis acid. So I'm going to use iron tribromide. We'll see with, for example, chlorine, it's usually aluminum trichloride. So usually what we're talking about is Lewis acids. Usually iron tribromide is paired with bromine, aluminum trichloride is paired with some of the others. But this is a Lewis acid, okay? And what happens, right? The way that you can sort of think about this, right, is that iron right, is going to, in essence, activate, it's going to serve as Lewis acid, it's in essence going to activate the bromine, okay? And what you're sort of making here is a molecule that might more closely resemble, let's see if we can, at least from a reactivity standpoint, and I'll show it this way and I'll explain why. right? Where if I, for example, coordinated and then had these electrons actually go and make a full bond there, right? You have a sort of a bromine positive, almost a bromine with a positively charged on it. If you're uncomfortable with that, we could also imagine it maybe like that, right? So that the leaving group is now a positively charged bromine, right? And so certainly that's going to maybe want to go away. And so whichever way that you're comfortable with drawing it, the idea here is that the iron tribromide is activating the Br2 and taking what is already a pretty good electrophile and making it even better. Okay, and this is going to be fairly common with all of the electrophilic aromatic substitution chemistry that we're going to see. You're basically taking an otherwise pretty good electrophile and you're going to make it an even better electrophile. And again, this is, you can rationalize the need for this just based upon the fact that bromine, or sorry, excuse me, that benzene is not your typical alkene, right? It's a much more stabilized version of it. So, okay, is this clear? Any questions? Okay, and so there's your first reaction from electrophilic aromatic substitution. I'm just going to erase this and show you the one that's basically the exact same thing. That's chlorine with aluminum trichloride. Come back to aluminum trichloride in a little bit. Basically, it's going to be the same concept, right? I'll maybe draw the aluminum coordinated here. Right, so the same sort of idea here, right? That you're coordinating, right? It's helping it leave, and then you're going to eventually re-aromatize in some way. So we can. So two of the classic examples, and I think two of the simplest ones to start with, in terms of electrophilic aromatic substitution, are halogenating benzene. Okay. Now, one of the things that I want to point out here that we'll come back to a little bit later on is you notice that I only put a single bromine on it, as I'm sort of showing right here, right? And when we think about the benzene ring, right, one of the things that maybe we're not necessarily discussing at this point in time is the impact of substitution on the nucleophilicity of aromatic systems. And so when we consider that we're putting a halogen onto this benzene, what do you think the impact of that's going to be on the electronics of the benzene? Yeah, Abraham.
Let's say bromine will pull away.
Yeah, exactly. So bromine and chlorine are certainly a bit electronegative. And so what these are going to do is they're going to, as Abraham said, they're going to pull electronics away from that benzene ring. And so you can often get sometimes selectivity. You don't necessarily, even though there's all these other alkenes, you could do follow-up reactions. When you're sort of putting on an electron withdrawing group, right, there's sometimes a benefit of that in that you're making the benzene itself less nucleophilic. And so this is one of the reasons why, for some of the chemistry that we talk about, especially early on, you can oftentimes control, if I just want to do one bromination, I could do one bromination. If I want to do two brominations, maybe I can push it a little bit harder, right? But I can control that and maybe not get tribromination, for example. So just something to keep in mind. All right, let's stick with I'll keep my aluminum trichloride there for now. Sometimes we can do chemistry, though, that becomes a little bit more challenging. I want to talk about this now. No, I'll hold off. I just want to go through the series of them for starters. Let me just start with Friedel-Crafts. I'll come back to Friedel-Crafts alkylation in a bit. But I'll start with Friedel-Crafts acylation. And so we're going to learn a couple of reactions. I'll start with acylation. I'll come back to alkylation. And maybe it'll be clear once I start talking about alkylation why I did this. But another reaction that you can do is called Friedel-Crafts acylation. Okay, which is going to differentiate it from Friedel-Crafts alkylation, as we'll see in a moment. The mechanism of a Friedel-Crafts acylation is going to be basically what we saw before, except that instead of adding a chlorine, we're going to add an acyl group, but the leaving group is going to remain the same. And so oftentimes when people talk about that sort of activation of Friedel-Crafts acylation, it always helped me. I always liked Friedel-Crafts acylation in terms of, I think, rationalizing the sort of activation of some of these electrophilic aromatic substitution reactions. Because if we do that same chemistry we did before, you can imagine drop the bonds. But you can imagine that that entire chloride can actually be pulled off the acyl group. And unlike that Cl plus or Br plus that we saw before, sometimes for whatever reasons having this resonance stabilized oxonium species is always something that was a little bit more comfortable to me when I saw it. And so in general, we consider this that sort of activated electrophilic source for Friedel-Crafts acylation. And the mechanism is going to largely be exactly what we saw before now, and that we're going to react. We can imagine, and I guess I didn't say this before, but we can imagine if we want that sort of conjugate base to re-aromatize, just so that we can sort of keep track of everything, we can kind of consider the equilibrium, right, between maybe AlCl3 and Cl minus to sort of give us back that Lewis base that we want to use as our to re-aromatize. But mechanistically, it's highly analogous. And we're going to see this for all the electrophilic aromatic substitution reactions. These are all going to be highly analogous, right? So we've activated the acyl chloride with aluminum trichloride previously. We activated the bromine with iron tribromide. We activated chlorine with aluminum trichloride. And now we're activating the acyl chloride, right, with the acid chloride, right, with aluminum trichloride. Okay, does this make sense? But again, mechanistically the same. We've activated it. The alkene is reacting, right? We when the alkene reacts, we leave behind this positive charge. We need to re-aromatize the system. Okay. Okay, and we're going to show two more. Okay. Before I get into Friedel-Crafts alkylation. We can actually add. We can make sort of sulfonic acids. Okay. In this case, right, what we're going to use is SO3. Okay. I'm going to make sure I get the reagent right. And usually there's an acidic source.
H2SO4.
H2SO4. Okay, so SO3 and in H2SO4, I guess this would be fuming sulfuric acid. All right. All right. And what's happening in this case, again, is we're activating it through bronzite acid, bronzite base chemistry, right? So we can imagine sulfuric acid leading to protonated version. Okay, so we're basically activating it, right? It's now a better electrophile. All right, we're going to attack. A lot of repetition here. I'm just doing the same thing over and over again. Okay. Something needs to come and deprotonate this. I had the sulfuric acid protonate it, so now we have, you know, whether it's the SO2, the SO3 can come and deprotonate it, or the sulfonate. It doesn't matter. For me, at least. Right? Same thing. So we've just seen 4 reactions. And hopefully all 4 of those reactions look the same. Okay. All right, so the last one that we're going to see before we get into Friedel-Crafts acylation will be nitration. Okay. Okay, and so for the case of nitration, what we're going to do is we're going to add a nitro group. Okay, it's worth actually drawing out the nitro group because that might look a little bit weird for you guys. I'm not used to seeing these sort of zwitterion molecules all that much, but nitro groups are sort of these stable zwitterionic forms. Okay. We're going to use nitric acid. This is nitric acid. Okay. Okay. And so from a mechanistic standpoint, again, what we're going to end up doing here is we're going to activate the nitro group. Okay. We're going to generate much like how we activated the sulfur over here. What we're going to do with nitric acid. A couple more step process. Now remember, everything's in equilibrium, so what I'm sort of drawing here is maybe not the kinetic, or what I'm drawing here is maybe not the kinetic protonations you might imagine. It'd probably be the O- that would protonate it, but these protonations are back and forth. Eventually, we're going to protonate this guy here. Okay. The reason why I want to do that is that the active form in this case is going to be this NO2 molecule that you see here. Okay. You guys, now this would attack this molecule. Maybe we can do the SO3 minus. Okay. To get to that nitro group. Okay. So 5 reactions. Okay. So every single one of these 5 reactions was the same thing, right? Chlorine, activate the chlorine, AlCl3. Bromine, activate the bromine with FeBr3. Right. Acid chlorides, activate the acid chloride with aluminum trichloride. So the SO3, right, to put on sulfuric acid, or sulfonyl, sulfonic acid, right? activate the SO3 with sulfuric acid. Put a nitro group, activate nitric acid for electrophilic attack with sulfuric acid. 5 reactions, Brianna.
The nitric acid originally has like the nitrogen has a positive charge as such. It's not a strong enough electrophile. We still have to activate it.
Well, where would you push the electrons? Right?
Yeah.
You attack that and then have to go somewhere else. So yeah, so this is just the established mechanism. Okay. All right, so in each of these cases that I just showed you, all 5 of them, I've sort of lumped them together, and I haven't talked about alkylation yet. In part because all 5 of them we're putting on electron withdrawing groups. A nitro is an electron withdrawing group, so over nitrating is going to be a little bit difficult. You can certainly do it under forcing conditions. I think that's how they make TNT, right? Trinitration. Could be wrong there. Sulfuric acid, trinitration, they don't like oxidize up the triamine. Okay, so JC knows how they make TNT, I guess. But again, because you're adding this electron withdrawing group to it, you generally only get that first addition. That can change a little bit when we get to groups that aren't electron withdrawing. This can be a little bit of a challenge when we get to groups that aren't necessarily electron withdrawing. And this can sometimes be an issue with, I generally don't dwell on this that much. If you actually look at my past lectures, I sometimes just ignore this altogether to make it a little bit simpler, but I'll mention it today. I think it's worth it, and then we'll get into how this impact has on electronics. But let's say that you have an alkyl group, a typical alkyl group like a methyl group or alkyl group, something that's not electron withdrawing, right? Your typical alkyl group. And you treat that with aluminum trichloride, right? Depending upon the nature of the R group that you have, you might get lucky and you might only get a single alkylation, or you may be able to control that. But as you can imagine, if you're starting to add alkyl groups to this, alkyl groups often, as I'll show you in a minute, they can increase the nucleophilicity of the benzene themselves. And so one of the big challenges that you can sometimes run into when you're doing Friedel-Crafts alkylation, which is what this is, is that you can get over alkylation of these molecules. So I've just sort of shown it in the middle because you can get a mixture of different places. But I thought this would be a good example to, I think, start to talk about sort of regioselectivity issues of when you're doing alkylation of perhaps non-benzene, like if you have substitution on it already and then you try to put another substitution on it. What are the things that dictate that? Because in principle, right, that alkyl group could be there, it could be there, or it could be there, right? It could be, remember what those terms were? It could be ortho, right? It could be ortho, right? Meta, and there's 2 ortho positions, there's 2 meta positions, and there's 1 para position. And just to sort of give you guys maybe something that's not just a generic R group, let's make this a methyl group just so that we can, let's imagine a scenario where we have the methyl group there already and we're going to add an additional methyl group. So we're going to start to get to various molecules. I'm going to start by just putting the methyl group on there just so that we can go through the regioselectivity of this. Okay. So we know that we want to activate this methyl group, right? And much like the acyl chloride, right, the chloride's going to abstract it, and so I'm going to do something that you're probably all so uncomfortable to do, which is have a primary methyl group. But I'm going to do it anyways, just to sort of illustrate how activated this is, right? And this benzene, right? Imagine the methyl group. Agora, you looked at me like that's uncomfortable to you. Oh, well, I should have gone with it and been like, yeah, I don't want to see a methyl group with a cation. But just to sort of illustrate how activated this methyl group is. that chloride has been pulled away by the aluminum trichloride, and so it's just a representation of an activated methyl group that we have here, right? And I'm gonna sort of, I'm gonna show a few different examples of this, okay? So if I were to add a methyl group to this carbon at that position, right? If I add the gem dimethyl, I'm not going to be able to re-aromatize. So really, the only position that I would have would be this one there. Let me ask you a question. Do you guys think that that's something good if we were going to attack? Does that seem like, how do I ask this? Do we like that? Any more than what we've seen in the past? Yeah, Christine.
That cause an elimination.
Well, eventually, yeah, we're going to do an elimination, right? So eventually we're going to eliminate, right? And that would lead us to, right, that would be our sort of ortho substitution. Do we like that, anything about that reaction? Leah?
Aren't they too close together?
Okay, so, well, that's a potential argument. Like, I don't like having those two methyl groups close to one another. Maybe, but so in general, when we start arguing, when we start talking about chemistry and we start thinking about selectivity of reactions, we're talking about sterics and electronics, right? So the steric argument might say, I don't like having two methyl groups next to one another, and that can be a factor that influences where groups go. Certainly, sterics can, in fact, influence that, and so sometimes getting ortho substitution can be a challenge because of sterics. What about electronics? Electronically, does that seem favorable?
Yeah,
Why?
because the alkene is more stable.
Why?
Because it's disubstituted.
Well, what's the transition state? What's the high energy, well, not necessarily the transition state, but what's the high, at least in terms of what I draw, what's the high energy species that I draw?
I'm gonna go with meta.
No. Sorry, what I'm asking is, I guess what I'm saying is this is the high energy speed. This is kind of the, yeah.
Does it have to do with aromaticity?
Not quite yet. We're going to regenerate aromaticity regardless, right? But there is something good about this that we weren't seeing in the previous examples. Brenda. Yeah, right? So Brenda nailed it, right? So that carbocation is tertiary, right? We didn't see tertiary carbocations before, and we like tertiary carbocations, right? So from an electronic standpoint, this is actually pretty good. You know, when we're trying to dictate whether it's going to go ortho, meta, or para, we kind of like that, okay? All right. Now, as we know, the sort of aromatic, I'm not going to go through it, we only got about 10 minutes left, but if we were to methylate the other side, we could have a resonance that could do the same thing. Maybe I'll have you guys consider that for home. Okay, but for this carbon here, unlike this one here, where if we alkylate it at the one position, we have the geminal dimethyl group, so we wouldn't be able to rearomatize. On this one, if we were to attack that carbon, we could put the methyl group on one of two carbons, right? We could put it on the carbon where it would eventually be meta, and we could put it on the carbon where it would eventually be ortho, right? Or sorry, para, thank you. So if it's para, right? We're going to put the methyl group there. We're going to put that there. If it's meta, we're going to put the carbocation there. Okay. All right, why don't we take a look at those two? Do we like either of them perhaps more than the other? Let's focus on the electronics here. Let's focus on those carbocations. do we like anything more about that carbocation than that carbocation? And the hint that I would give you guys is it's not necessarily something that I would expect you to just look at really quickly and see. You have to do a little bit of work here to see the real electronic difference between those two. Christine?
Does that have anything to do with hydride shift?
So there's not going to be any hydride shifts here. You don't have to do a hydride shift. Yeah, Abraham.
Is that one's meta and one's para?
Well, that's a circular argument, right? We told you that one's meta and one's para. What is it about the carbocation nature when one goes ortho and when one goes meta and one goes para that might make one happier than the other? Yeah.
Is the power one more stable because there's metals on both sides?
No, that's kind of a circular argument as well, right? Right. Para reflects that they're on both sides. Yeah, Mike.
Isn't that when the methyl is on the para section, you could eventually make a resonance structure for the carbocation to be the tertiary one, but with the second one you can't?
Bingo. See that? So there's a resonance form here. Right? So there's a resonance form there, right, that if we were to move those electrons over to that carbon, we get back to that tertiary carbocation there. You guys see that? Right? If we try to do the same thing here, we can't do that. Right? I'm going to move it there, and we'll keep walking this around. Right, if I move that there, I'm going to put it there. If I try to keep going, right, I'm going to put it right. See, I put it on both sides, and you guys can oops, sorry. Right, and I can what did I do wrong here? Right. So and we can keep trying to walk this around, and we'll see that we'll never be able to put that carbocation on that sort of tertiary one there. Okay? And so, in general, this is an important concept in terms of, and it's certainly one of the things that you guys need to know, and it's the fact that when you're doing, well, let's just go back to the sort of final part of this story, right? This is going to go ultimately to the para product. Para. This one's going to go to the meta. And this will be the ortho. Right? So we have these three possibilities, right? And of the three, which might we guess would be the major? Or which two? Or which one would we guess would not form, for starters? Maybe we should start there. The meta one would probably be the least likely to form, right? And in terms of happening, that would be the case, right? That's not going to form. We're not going to get meta selectivity here, right? Because the meta group, you can't stabilize that cation. Now we'll get back to this. This is we're talking about a donor group here, right? Things will change once we get to some other groups, but at least when you have a donor group like a methyl group on there, it's not going to direct at methyl. It's not going to direct at meta, excuse me. Okay? Any differences between the ortho and para that we can see?
Well, there's two possibilities in the ortho.
Yeah, I think exactly. Well, so with the ortho, there's two, right? There's two carbons. So statistically speaking, right, you might expect to get a 2-to-1 ratio just based upon electronics. Maybe it'll shift based upon sterics, a little bit maybe closer in the other direction, right? But we're probably going to get a mixture of these, right? We're probably going to get a mixture of ortho and para. And what extent we get that mixture is probably going to have to do with conditions, or for example, sterics of these, right? If these groups are bulkier, maybe it'd be less likely to be ortho, right? Maybe they'd be more likely to be para based upon sterics. And so this is one of the things that we're going to get into. It's probably done with time. This is one of the things that we're going to start to get into. So Friedel-Crafts alkylation is a good example to start to begin to get into this story. But Nima, did you have your hand up? Or? Okay. All right. Any questions about this? Okay. So we're sort of taking this with the standpoint of Friedel-Crafts alkylation, where we're adding the same thing. But for example, in synthesis problems, right, we can use a whole bunch of these reactions, right? And so you might imagine the same thing, right, would hold true if we did, say, for example, if we had, right, this sort of ethyl group, right, and we try to treat it with, I don't know, let's say SO3 and sulfuric acid, or any one of those other ones that we saw before, right? And what's going to happen, right, is we're going to get a mixture of products, right? And because of the fact that this is a donor group, right, we're probably going to get a mix of this plus this. Okay. But what if I didn't want those? What if I wanted this? Right? What if I wanted the meta? Right? So we've sort of established that when you have this donor methyl group, right, and we treat it to electrophilic aromatic substitution, we're going to get some mixture of ortho and para. And again, that could maybe be dictated by sterics or otherwise. The question is, how would we make this? And the question would be, how would we make that? And there's a couple of ways that we could do this. Okay, and the first is, I think the overall point that I'm trying to make here is that if you have a donor group, right, a resonance donor group, you're going to be ortho-para. But in general, and we'll see that this isn't the case for halides, if we were to swap these reagents and say, for example, had a sulfonate or sulfonic acid on there already, and let's say, for example, that we tried to switch the two, right? Now instead of a donor group, our aromatic ring has an electron withdrawing group, right? And if we consider the possibilities, as I'm drawing this around quite a bit, right, just for the sake of time. I'm just going to show the cations, okay? Because as we sort of saw previously, it's the cations, it's an electronically driven process. So the question sort of becomes, what's the difference between these two? And it's best to start with looking at that one right there. You know, before we had a donor group, now we have an SO, sort of a sulfonyl chloride. Sorry, sulfonic acid, excuse me. And we look at that molecule, and you know, I think one of the things that's sometimes difficult to see is we assume, oh, substitution is good. But what we try to avoid in general is having electron-deficient groups next to another electron-deficient group. And when we consider this sulfonic acid here, what's the most electron-deficient part of a sulfonic acid? The sulfur, right? Sometimes we even draw, and sometimes people will often draw sulfonic acids with a 2+ charge on the sulfur. You guys ever seen it done this way? Where it's 2+ on the sulfur, O-, O-. Have you guys ever seen it drawn that way? Well, you haven't. Sometimes you do, right? But the sulfur is the electron poor part to this. You have a withdrawing group there, you have a withdrawing group there. So that sulfur is extremely electronically poor. And what that means is that you're not going to want to have a positive charge adjacent to it. Does that make sense? Right? So it's kind of the opposite of what we saw before with the alkyl group. The alkyl group stabilizes it. A sulfonic acid will destabilize that same position. Okay, to either of these, based upon what we saw before, that's ortho. Here's our para. What do you notice about our para? That resonance does what? It puts that carbocation in the same place that we didn't like having it up there. It's tertiary, but it's not a good tertiary, right? You put it next to this electronically poor sulfonic acid. And so, turns out that's bad. That's bad. And so this, I guess I'll go right to it. It's flipped upside down, but just to avoid board space. You do the elimination and you get there. So when you have a resonance withdrawing group, okay, such as this, where you have that portion of the sulfur, right, that's going to be a meta-director. Okay. Other meta-directors, a nitro group is a meta-director, which we saw, and an acyl group. Right, and these are both, right, these acyl groups, right, the acyl group, right, you have that delta positive, right, at that carbon, right, which would be right next to it. Right, that nitro, right, that's where we have that positive charge. So now you put the two positive charges next to each other. Right? The one that I haven't shown here among our electron withdrawing groups, though, is halogens. Okay? And we'll start, I guess, with that on Monday. Okay? Or just think about why would a halogen, on Monday, we'll start with that, but think about that before Monday. Why would the halogens are going to be orthopara, and we'll start with why that is on Monday, or on Wednesday.